Have you ever wondered how living in zero gravity could affect the human body? In the vast expanse of space, there exists a fascinating phenomenon known as zero gravity. It's a place where the force of gravity is so weak that objects and astronauts alike seem to float in midair. Now imagine you're an astronaut embarking on a journey to the stars. You're exposed to this strange environment where the normal rules of up and down no longer apply. Over time, living in this zero-gravity environment, or microgravity, as scientists prefer to call it, can cause significant changes to the human body. Our bodies, after all, evolved under the constant pull of Earth's gravity, and removing that force can have some rather unexpected consequences. So, you might be wondering, what exactly happens to the human body in this zero-gravity environment? It's a question that has intrigued scientists and space enthusiasts for decades. But what exactly happens to our bodies in zero gravity? Let's delve deeper. When humans step into a zero-gravity environment, the first system to be affected is the musculoskeletal system. Our bodies are remarkably adaptable, evolving over millennia to thrive under the steady pull of Earth's gravity. But when we venture into the weightless expanse of space, our musculoskeletal system, which includes our muscles and bones, finds itself in uncharted territory. In the absence of gravity, there's a significant reduction in the load our muscles and bones have to carry. Sounds relaxing, right? Well, not quite. Our bodies operate on a use it or lose it principle. Without the everyday stress of gravity, our muscles don't receive the regular workout they're accustomed to, leading to a condition known as muscle atrophy. This means our muscles start to waste away, losing mass and strength. Muscle atrophy isn't the only concern. Our bones, too, suffer in a zero-gravity environment. They are dynamic structures, constantly breaking down and rebuilding. On Earth, the process is balanced, but in space, without the regular stress of gravity, bone breakdown outpaces its rebuilding, leading to a decrease in bone density, a condition perilously similar to osteoporosis here on Earth. This loss of bone density doesn't just make astronauts more fragile. It also increases their risk of fractures, not just in space, but also when they return to Earth, where their weakened bones must suddenly support their full body weight again. What's more, the calcium lost from the bones is eliminated in the urine, increasing the risk of kidney stones. Not a pleasant prospect for anyone, let alone for individuals confined to the limited facilities of a spacecraft. To counteract these effects, astronauts follow rigorous exercise routines in space, using specially designed equipment to simulate the effects of gravity. But despite these measures, full recovery of muscle and bone loss can take a long time, and in some cases may never be complete. In essence, without gravity, our bones and muscles start to deteriorate. This is the stark reality faced by space scientists returning to Earth after a stint in zero gravity. It's a sobering reminder of how deeply our bodies are tied to the gravitational forces of our home planet. Our hearts and blood vessels are not spared from the effects of zero gravity either. Imagine a world where gravity doesn't restrict the flow of fluids within our bodies. In such a world, the fluid in our bodies would redistribute evenly, and this is exactly what happens in space. The redistribution of fluid away from the legs and towards the upper body results in a condition humorously referred to as puffy face and bird leg syndrome. Astronauts often have a swollen face and skinny legs due to this fluid shift, but it doesn't end there. The heart, a muscular organ, adapts to this new fluid distribution. In the absence of gravity, the heart slowly loses its elongated shape and becomes more spherical. This change is not only cosmetic, it affects the heart's function as well. The spherical heart has a different pumping efficiency compared to its original shape, which can lead to a decrease in the heart's overall performance. Another fascinating change occurs in the regulation of blood pressure. On Earth, our cardiovascular system works against gravity to ensure blood reaches every part of our body, especially the brain. However, in zero gravity, this is no longer necessary. The body responds by lowering the blood pressure, a condition known as orthostatic intolerance. This can lead to dizziness and fainting spells, especially when astronauts return to Earth's gravity. Furthermore, the walls of the blood vessels may also thicken in space. This is thought to be a response to the increased blood flow in the upper body. However, it could potentially lead to issues like atherosclerosis, a disease where plaque builds up inside your arteries. In essence, our cardiovascular system is designed and optimized for life on Earth. When we venture into space, the rules change and our bodies must adapt. This adaptation can lead to some intriguing and sometimes concerning changes in our physiology. Thus, zero gravity can literally reshape our hearts and disrupt the way our blood circulates. The nervous system also undergoes fascinating changes in zero gravity. Our brain is an exceptional organ, constantly adapting and recalibrating based on the environment. In zero gravity, however, it faces a unique challenge: our sense of spatial orientation, which allows us to perceive our position relative to the world around us, is thrown off in a weightless environment. This can result in disorientation and a loss of balance. Similarly, hand-eye and head-eye coordination, crucial for our day-to-day activities, are also affected. Without the familiar tug of gravity, our movements can become uncoordinated and clumsy. Interestingly, many astronauts experience something called space adaptation syndrome, a condition that resembles motion sickness on Earth. It's a clear sign of the nervous system trying to adapt to the new environment, but it can lead to nausea, dizziness, and even a lack of mobility. Therefore, zero gravity can turn our sense of orientation and mobility upside down. So, living in zero gravity can significantly alter our physiology. We've ventured through the body, from the musculoskeletal system, where we've grappled with muscle atrophy and bone density loss, to the cardiovascular system, where we've tackled the redistribution of blood and a decrease in blood volume. We've also navigated the labyrinth of the nervous system, understanding spatial disorientation and sensory perceptions in a weightless environment. We've unearthed the stark reality of zero gravity's impact on the human body. It's a captivating paradox, isn't it? The weightlessness that enables the awe-inspiring sensation of floating in space is the very same force that triggers these physiological changes. While the prospect of exploring space is exciting, it's clear that zero gravity presents a host of challenges to our bodies. As we continue to push the boundaries of space exploration, understanding and mitigating these effects will be crucial for the health and safety of our astronauts.